So good day guys. So today in this video we are going to be talking about entropy and how entropy depends on volume, pressure and temperature. Those are the major things that we are going to be talking about in this video. But before we start proving how we can get a formula for entropy that is depending on both volume and temperature and volume and pressure, let's first get what entropy means. Actually, we define entropy as a degree of disorderliness of a system. That means as we are changing from one particular state of matter to another, we are either increasing the entropy or decreasing the entropy. For instance, if we are changing from solid to liquid, we are actually increasing the entropy. And if I'm changing from liquid to gas, at the same time I'm increasing the entropy. And as I'm increasing the entropy, it's more like we can say the particular system is said to be spontaneous. Increasing entropy will actually lead to increase in spontaneity of that particular reaction. But if we are changing from gas to liquid, we are actually decreasing the entropy of the system, and thereby the probability of that particular reaction going to completion cannot be guaranteed. Do you understand? So good. So now let's move on to how we can get a formula that will be relating entropy to volume. Now don't forget, in this video we're actually getting this formula from first law of thermodynamics. So from first law of thermodynamics you can say, okay, Q is actually equal to du plus dw. Good. From first law of thermodynamics, that means Q is change in Q, or let's say Q is equals to change in U plus W. Now this Q talking about the quantity of it, our U here is actually talking about the internal energy, and our W is what is the work done. So good. Now we should not forget that for a reversible reaction, a reaction that the change in system is actually very small, negligible, we can actually see our ds is actually equal to the qv, that's reversible over t. Yes, for a reversible reaction we can say our change, the air, that's t, entropy is equals to the q over what over the t for a reversible reaction. Okay, now let's take note of that because we are going to be needing this formula as we move on. Good. Okay, now from this particular formula, let's say, don't forget that what I want to get is actually a formula that will be relating this. We are starting from entropy, volume and temperature. So those are the major three things that we want to bring out from this first law. So with this formula I know that, okay, I can divide all through by t. Let's divide all through by t. So if I divide all through by t, from here we can actually denote that, okay, this what I'm having here is actually going to be ds, right? So I'm going to be having ds is actually equal to, we have du over t plus dw over t. Okay, good. Now what will I do to make this thing look like volume? We should not forget that at constant volume we can see our du is actually equal to cv, that's molar heat capacity at constant volume dt. If you check the video before this video, we actually got the formula for cv, that cv is equals to du over dt when volume is what is constant. So I've gotten a formula for du, and then my dw, now dw is actually equal to p dv. We should not forget that the formula for w, normally my w is equals to p changing what, changing v. So now since I'm putting w at the front, it will be what, p dv. So okay, let's now substitute each of them inside this particular formula. So good. So moving on, I'm going to be having my ds is equals to, instead of du now I'm going to be having cv dt over, I'm having t at the down, plus, now instead of dw I'm going to be having what, the p dv, over what? Over t. So this is what I'm having here. Okay, good. After this, don't forget I'm actually trying to get a formula that will be relating my entropy to my temperature to my volume. So what's actually giving me an issue here is my P. I don't want to see P there. I want to change it to volume. Now from Gauss law, we know PV is equal to what? nRT. Good. So and now we are talking about just one mole when n is equals to 1. So automatically I can say, okay, my P is actually equal to root T over what? Over V. So instead of writing this P there, I can actually replace this P with this. So let's move on with that. Let's get that. Good. Okay, with that now I can say, okay, my ds is actually equal to cv dt over t plus, instead of my p, I'm having rt over v to multiply the v over what? Over t. So this t can actually cancel out this t. So I'm going to have my ds is equals to cv dt over t plus I'll be having r dv over what? Over v. So this is what I'm having. So what can I do next? Now with this, now don't forget I'm looking for change in entropy, and then I want to relate it with my volume and my temperature. So all these dt, all these dv, ds, I don't actually need it. So how will I remove them? I have to integrate. So let's integrate. ds is equals to, I'm having the cv dt over t plus the integral of r dv over what? V. So we're talking about two different volumes. We have v2, v1 within the interval of two volumes. This one will be within the interval of what? Two temperatures. Good. And this is just changing what? Entropy. So if I should integrate ds, what I'm going to be having, if I integrate ds, automatically I'm going to be having change in s. So I'm having change in s is actually equal to, now my cv is constant. I can bring out my cv out. If I bring out cv, I'm going to have t2 t1 dt over t plus r is also constant. If I bring out r, I'm having v2 v1 dv over what? V. So I'm going to have change in s now to be equal to, I will have cv. If I integrate 1 over t, you are going to mean that I'm going to have ln t. So I have ln t, we have t2 t1 plus this will give me r. Also if I integrate 1 over v, automatically I'm going to be having ln v. Ln v, we have v2 and what? V1. So if I move further, let me try to bring this. If I move further, I'm going to have change in s to be actually equal to cv. Then I will have ln t2 minus ln t1 plus I will have r open brackets ln v2 minus what? Ln v1. And this is actually equal to, change in s is equals to cv. Ln t2 minus ln v1 is same thing as ln t2 over what? T1. Since both of them are ln, so bring out this minus 20 to divide, plus I will have my r, I will have ln, the same thing too happens here, I will have v2 over what? V1. So with this formula, we have actually gotten a particular equation that is relating change in entropy, temperature, and what? Volume. So at this instance, we can see that if volume changes, it will affect the value of what? Of the entropy. So this is how to actually get a formula that shows that change in entropy depends on temperature and volume using first law of thermodynamics. Okay, good. So we have gotten that, but we are not through. We are still actually looking at how we can actually relate this to pressure. So how can we get that? Okay, same from gas law, general gas law, we know that P1 V1 over T1 is equals to P2 V2 over what? Over T2. So now let's try to find a particular equation to replace this v2 over v1. So what I'm saying is, let's make v2 over v1 the subject of the formula. If I should cross multiply, what I'm going to be having is p1 v1 t2, sorry, Good. Okay, so if I'm going to be having, this will be T2 to be equal to, here I'm going to be having P2 V2 T1. Don't forget, what I'm looking for is V2 over V1. So I'm going to divide both sides by P2 and T1, also divide this by, so what I'm going to be having is P1 T2, sorry, over, then I'm going to be having P2 T1 to be equal to, we have V2 over what? Over V1. So I've gotten a particular equation that is actually relating V2 over V1 to P2 and P1 over P2 and T2 over T1. So instead of this particular equation I have here, instead of this V2 and V1, I can actually replace it with this. So let's try to do that. Let's see what we are going to get. So I'm going to have change in S is equals to, we have CV lane. I'm still having my T2 over T1. Good. Plus, then we have arrow lane. Instead of my V2 V1 now, I'm having P1 T2 over, we have P2 T1. Good. So this is what I'm having. So let's try to work with this. So with this now, what I'm saying, okay, what we are trying to say is we have change in S to be equal to, we have CV lane T2 over T1 plus, then I have arrow lane, we have, okay, I can have P1 over P2 to add up with arrow lane T2 over T1. Don't forget that this particular thing here is still equal to what we have here. They're actually equal. So because this arrow and lane are they are similar, so I can just bring up one and then use the P2 to multiply P1 to multiply T2 and P2 to multiply with T1. Okay, good. So this is what we have. You can see that this is lane T2 over T1 and this is also lane T2 over T1. So we're having something in common. So I can actually say, okay, my change in S is actually equal to, now, but we're having CV and R here. So we can say, okay, CV plus my R, then I have lane, we have T2 over what? T1. Very good. So I have T2 over T1 plus, now what I'll be having left is my arrow lane P1 over what? Over P2. Good. So this is what I'm having. Now don't forget, in the last video we actually got CP to be equal to CV plus R. Good. So instead of this CV plus R, we can actually replace it with CP. What is CP? CP is actually the specific molar capacity at constant pressure. So that's CP. So we can just say our change in S is equals to, we have CP lane, we have T2 over T1 plus we have arrow lane P1 over what? Over P2. But okay, then I can actually write this equation to be like this: CP lane T2 over T1 minus arrow lane P2 over what? P1. So just bringing this up, so I have to integrate and to show the negative sign that will show when I bring this P2 up. Okay, good. So you can see that at the end of the day we have gotten an equation that is actually relating our entropy to pressure and to temperature. And don't forget, we also get an equation that is relating change in entropy, temperature, and what? And volume. So we can see that from first law of thermodynamics we can actually show that change in entropy depends on temperature, depends on volume, and also depends on what? Pressure. Should we get good? Okay, so we have gotten the major formulas relating changing S to temperature and pressure and to volume. So let me quickly write those ones for volume at the down parts since we are going to be needing it. We have CV ln, we have T2 over T1 plus we have arrow ln, we have V2 over what? V1. So there, at constant volume, at constant volume, what will be the equation for changing S? We should not know that, we should not forget that at constant volume, sorry please, at constant volume, our V2 will actually be equal to what? V1. So if V2 is equals to V1, so automatically we can see our change in S is actually equal to CV ln, we have T2 over T1 plus we have arrow ln. Now V2, let's just V2 over V2 since they are equal, so it will be cancelling. So we have change in S is equals to CV ln, we have T2 over T1 plus we have arrow ln 1, and the 1 is equals to what? 0. So we can actually conclude our change in S is actually equal to what? CV ln T2 over what? T1, since this will actually be equal to 0. Do we get that point? So take note that at constant volume, our change in S is equal to what? CV ln T2 over T1. What about at constant temperature? Let's actually work it together. Let's put it somewhere. Yeah? Good. So at constant pressure, so at constant pressure, we should not forget our P1 will actually be equals to what? P2. So if P1 is equals to P2 and we have change in S to be equals to, we have CP ln T2 over T1 minus we have arrow ln P2 over what? P1. So automatically I can say my change in S is equals to CP ln T2 over T1, since eventually this is going to be equals to what? 0. Do you understand? Because they will eventually cancel out, we have ln 1, so I will ln 1, everything will be equals to 0. So at constant pressure, this is actually going to give us change in S equals to CP ln T2 over T1, and at constant volume we are going to be having this our change in entropy. So we should take note. So what about at constant temperature? So at constant temperature, we can actually have two particular formula for change in S. Either we are relating with CP or we are relating with what? With CV. So let's start with CV. So we should not forget our change in S is actually equal to CV in T2 over T1 plus we have arrow, sorry, good. Right, so arrow we have ln, sorry, done. We have ln, we have V2 over V1. So with that now, so we can actually see our change in S is actually equal to CV ln 1 plus we have arrow ln, we have V2 over V1 at constant temperature. Good. So at constant temperature, we should not forget our T2 will be equals to what? T1. Very important. So automatically we have our change in S to be equals to this will be equals to 0. So we have our arrow ln V2 over V1. So we can see that at constant temperature, we can actually relate our change in S in terms of volume, whereby our CV will be equals to 0 since it's multiplying ln 1. So we are having this change in entropy in terms of volume. What about if we want to have it in terms of temperature? The same way too. We are just going to say, okay, our change in S is equals to, we have CP ln our T2 over T2, since T2 is equals to T1, good, minus arrow ln, then we have P2 over what? P1. we should not forget this is at constant temperature. Good. At constant temperature. So automatically we are going to be having our change in S to be equal to Cp ln 1 minus Rho ln, we have P2 over what? P1. So we have change in S to be equal to this is going to give us 0. So we are going to have Rho minus Rho ln P2 over what? P1. So you can see the formulas that we actually arrive at. So at constant temperature we can have this particular formula for change in S, or we can equally have this depending on what we are relating it with. Are we relating it with volume, or we actually relating it with pressure? So if you are relating it with volume, we know we have this, and if you are relating it with pressure, we actually know we have this. So that's it. So let's take notes. Good. Okay, so we have gotten our changiness in terms of volume and in terms of pressure at constant temperature. Good. Okay, so let's move on to the next part. Okay, so now the next part that we are going to be checking out now is when they give us our CV or CP in terms of temperature, and they ask us to look for our changiness. So they give us our CV or CP in terms of temperature, and ask us to look for our changiness. How are we going to do it? Now let's check out a formula that we can use in solving something like that. Okay, now we should recall that from the beginning of this class we already said our ds is actually equal to dq over what? Over dt for reversible reaction. Okay, good. So we got that. Now we can actually conclude that this at constant volume is actually equal to CV. Good. CV dt over T, because at constant volume our dq is equals to ZV, our dq here is equals to CV dt. Okay, so we have gotten that. Now I can now relate this one to this. So let's relate the two of them together. I'm going to have the S is equals to, the S is actually equal to, we have CV dt over what? Over T. So let's now integrate. Okay, if I integrate this ds, I'm going to have, we have CV, the integral of CV dt over what? Over T. But now our CV now is now depending on temperature. That means you can see our CV is actually equal to A plus BT plus CT square, and so on and so forth. So this is going to give us changiness. We have to do for it. This is interval to temperature T2 and T1. So I'm going to have this to be, our change in S to be equals to the integral of T2 T1. So instead of this CV here, I'm going to be placing it with what I have here. So this will be A plus BT plus CT square, and if I have more, dt, everything divided by what? T. So if I break it down one by one, then I'm going to have my changiness to be equal to the integral of, we have T2 T1, we have A over T plus, this is going to give me just my normal B, plus this is going to be my CT dt. Good. So because I divided through by T, so now I'm going to have my changiness now to be each equal to, now let's integrate. If I integrate this, I'm going to have A ln T, because if this is A is a constant, if I integrate 1 over T is going to give me ln T plus this is t raised to power 0. So if I integrate t raised to power 0, automatically I'm going to have what? bt over 1. So plus, if I should integrate this, I'm going to have ct square over what? Over 2 if I integrate t. Now don't forget that this is interval of what? 2 temperature, T2 and what? T1. And don't forget that this is actually at constant volume, so I'll put it as CV, CV and CV. Since we are talking about the change in entropy at constant volume, so this is an expression that we can use to calculate change in entropy at constant volume, whereby we are given CV in terms of what? Temperature. Okay, we can also do this too in terms of pressure. How? Let's try that. Good. Okay, we also start from this particular point too. So at this particular point, we can see our ds. Don't forget our ds is equals to the QV for reversible reaction over temperature, and this is actually also equal to Cp dt over what? Over T. So I can actually relate these two things together. If I'm relating this, I'm going to have ds is equals to, we have Cp dt over what? Over T. So with this now, we have given our Cp to be in terms of temperature. That means we have A plus Bt plus Ct square and so on and so forth. So if I should integrate this, the integral of ds is equals to the integral of, instead of this Cp now, I'll be replacing it with this. So I'm going to have A plus Bt plus Ct square dt, everything over what? Over T. Is actually almost the same. It's not even almost the same method that we actually use in getting the change in entropy at constant volume. So we're going to just apply it to here. So here I'm going to have change in S, but now it will not be V again, to be at constant pressure, is equals to, don't forget this is at interval of 2 temperature, T2 and what? T1. So here I'm going to have A over T, the integral at T2 T1 over T, plus I'm having Bt over T is actually going to give me just B, plus Ct square over T is actually going to give me Ct dt. So if I now integrate, so I'm going to have change in S to be equal to, I'll change in S to be equal to, I'm going to have A ln T plus, I'm going to have Bt plus Ct square over 2. Now 2 temperatures, which is T2 and what? T1. So this is actually Cp. So we have gotten a particular formula that we can use to calculate change in entropy at constant volume, whereby our Cp is given in terms of temperature. The same thing too, we can also look for our change in S at constant volume too, whereby our Cv2 is also given in terms of what? Temperature. So these two formulas, we can actually use them, whereby our Cp and Cv is given in terms of temperature and pressure. And don't forget our A are constant, and they depends on the nature of the substance that are involved in that particular reaction. So these are the formulas that we are using. So our next video will be based on how we can actually relate our entropy to melting point and boiling point. So check out the next video on how we can look for change in entropy relating to melting point and boiling point. Thank you for watching this video. Don't forget to like and subscribe. Thank you.